Hi everyone. Let's talk about the theory behind the quantum rotor experiment. This theory is also covered in the lab handout and indeed in many textbooks on quantum mechanics and physical chemistry. Okay, let's have a look. All right, so we'll start by describing the energy levels in molecules. And here, we're actually interested in just a particular type of energy, which is the energy associated with the motion of the atomic nuclei, or the atom cores in the molecule. So imagine a molecule like this simple diatomic molecule here, consisting of, you might imagine, the atomic cores surrounded by a cloud of valence electrons. Then we know that there are different types of motion associated with this molecule. The atoms might vibrate against each other, and the whole molecule might rotate. In addition, we could excite just the electrons into higher molecular orbitals, but we're not interested in that today, just vibration and rotation. To a first approximation, the bond between the atoms can be thought of as a spring, with some spring constant K. And the atoms have some mass, M1, M2, for this diatomic, and thus some reduced mass. And for vibrational motion, we can think of this as like the motion of harmonic oscillator. In addition, the molecule can rotate. For a diatomic molecule, there's only one type of rotation, and that rotation about the bond is shown here. And then the system can have rotational kinetic energy. Okay? So we can get expressions for vibrational and rotational energy, okay, which look like this. So here, the vibrational energy is quantized in units of h bar omega, and where omega is the natural frequency of the oscillator. And in this expression, nu is a quantum number, which can take on values 0, 1, 2, 3, and so on. The rotational energy, in contrast, is given by this expression. It's h bar squared over 2I times j plus 1, where I is the moment of inertia of the molecule, and about this axis. And j is a separate quantum number, which takes on the values 0, 1, 2, 3, and so on as well. Okay? And the total energy would be the sum of these. And something we want to keep in mind is how this looks. Let me make a diagram here, and please bear with me. It'll take me a moment to make it. Typically, the spacing between the vibrational energies is much larger than the spacing between rotational states. And so the energy states look like this. where these are states with nu equals 0, 1, 2, 3, and so on. And of course, the states are equally spaced. However, if we look closely, we'll see that each of these seemingly solid bands is in fact divided into rotational states that are closely spaced. And so we'll have rotational levels that look like this. And so on. The important thing is that the spacing between vibrational states is typically on the order of 1/10 of an electron volt, something like that. Whereas the spacing between rotational states might be of the order of 1,000th of an electron volt. Anyway, it's on a smaller energy scale. Okay.